punchline for this lecture. Punchline. Okay, so we're going to answer how good is the expected value as, representing or summarizing the outcome of an experiment. How good is the expected value of x for summarizing the experiment. And it turns out that we're going to use the standard deviation here. Remember, that's the square root of the variance. So, theorem. Okay. So you have a random variable x. Okay. And, you can compute its expected value. You have the expected value of x. Let's call this mu. And you have the standard deviation. So the square root of the variance of x. This is sigma. Okay. Now you run your experiment and you see what's the value of x, what's the value of your measurement. And here's what we can say. We can say that most of the time, so approximately 90% of the time, and you can make this number 99% if you want, you can make it 99.9%, okay, and so on and so forth. Approximately 90% of the time, the value you observe for x, so the value you observe for x will be equal to, mu plus or minus 3 sigma. Okay. So that means that the range for x, mu minus 3 sigma to mu plus 3 sigma, is the range for x. 90% of the time. So 90% of the time when you run the experiment, you will find that the observed value of x will be within 3 standard deviations of the mean. And it is in that sense that the mean is a good estimate of the outcome of the experiment. It's a good summary of the experiment. So it's going to be a better and better summary. It's going to be a more and more accurate summary if this is not 36, this is sigma. This is sigma. This is sigma. It's going to be a better and better summary of the experiment when the standard deviation is small. Okay. So this is called the 3 sigma rule. Okay. Mean expected value plus or minus 3 sigma is the range in which the random variable will lie with high probability. Okay, and now let's prove it. And to prove it, I'm going to show you 2 important theorems in probability theory. Okay, they are important on their own, but we're just going to use it to prove the 3 sigma rule. So that's the punchline. It says that when the variance, when the standard deviation is small, the mean is a great summary of what will happen. Okay, and so let's do the proof. Okay, so there are 2 steps. Okay, the first is sometimes called Markov's inequality. So we'll start with Markov's inequality. They're not hard. It's just, it's kind of ingenious that these guys thought of these. And then the second is what's called Chebyshev's inequality. Okay, so let's just derive both of these inequalities. So let's look at, the expected value of my random variable x. What is it? Okay, it's equal to the sum over the possible values of the value times the probability. Now, let us suppose that the possible values are all positive. So there are are all non-negative. So there are no negative possible values. So we call this a positive random variable. So, assume x is greater or equal to 0. So it can never be a negative value. In which case, if we remove a part of this sum, you have to get something smaller. So this is at least as large as when I sum over the possible values that are greater than alpha. Okay? For any alpha bigger than 0. So it's at least as large as this, the full sum is at least as large as the partial sum, where I only take the possible values that are greater than or equal to alpha times x p of x. Okay. But now, in here, x is always greater than or equal to alpha. So this is at least as large as the sum over x greater or equal to alpha of alpha p of x. And that's because x is always greater or equal to alpha. Okay. And then this is equal to alpha, the sum over all the possible values x greater or equal to alpha, p of x. Okay. And that's because alpha is a constant independent of x, the summation index, so I can pull it out. Okay, and this is the sum of the probabilities, okay, for all the possible values of x that are greater than or equal to alpha. So this is alpha times the probability that the random variable x is greater or equal to alpha. Okay. So if you have a non-negative random variable, so we typically just say positive random variable, assume that you have a positive random variable, then, okay, the probability that the random variable exceeds alpha, the probability that x is larger or equal to alpha is at most the expected value of x divided by alpha. So, what's the important punchline? The important punchline is the 3 sigma rule. Mu plus or minus 3 sigma is what you will see 90% of the time. Okay, and it looks like we're proving something totally unrelated. That this is called Markov's inequality. If you have a positive random variable, the probability that that random variable exceeds any fixed alpha, you get to pick whatever alpha you want, is at most its expected value divided by alpha. Okay, that's called Markov's inequality. And now I'm going to prove Chebyshev's inequality. So the proof of Chebyshev's inequality is as follows. Okay. So let us consider, okay, the probability that the absolute deviation, okay, so let me write this. Let us consider the probability that the random variable x minus mu minus its expected value. Let's consider the probability that this is larger than or equal to t sigma. So some multiple, which I'm calling t times sigma. Okay. So let's consider this probability that there's a large deviation between the random variable x and its mean. Okay. Well, if the deviation is large, if this deviation is larger than t sigma, then that is the same as the probability that the deviation squared is larger than t squared sigma. X minus mu squared is larger than or equal to t squared sigma squared. Okay. And x minus mu squared is just the deviation squared. Okay. So let me define a random variable y, which is x minus mu squared. Okay. Then the expected value of y is the expected value of x minus mu squared. Okay, but that's just the variance of x. This is just sigma squared, the variance of x. Okay, so the probability that y is greater or equal to t squared sigma squared is at most the expected value of y divided by t squared sigma squared. Divided by t squared sigma squared. Okay. But the expected value of y is just sigma squared. So this is equal to sigma squared over t squared sigma squared, which is 1 over t squared. Okay. So what is this saying? This is saying that the probability that y, okay, the squared deviation, is greater than t squared sigma squared is at most 1 over t squared. But the probability that y is greater than t squared sigma squared is exactly this probability, which is exactly this probability. So Chebyshev's inequality, which we have proved, is the following: that the probability that x minus mu is greater than t sigma is at most 1 over t squared. So I'm going to box these. Okay, this is an important inequality on its own right, but we mostly just used it to prove Chebyshev's inequality. Okay. So let's plug in t equals 3. When t equals 3, the probability that x minus mu, so the probability that x deviates from mu by more than 3 sigma, the probability that x minus mu is greater than or equal to 3 sigma is at most 1 over 3 squared, 1 over 9. Okay. So this 1 over 9 is a little bit, larger than 1/10. Okay, so the probability that x minus mu is less than 3 sigma is at least 1 minus 1 over 9. Okay. 1 minus 1 over 9 is 8 over 9. This is 8 over 9. This is approximately equal to 89%. Hence I said approximately 90%. And what is this saying? This is saying that the probability, the chances that you see a deviation that's less than 3 sigma is at least approximately 90%. So you will rarely see deviations that are larger than 3 sigma. That's the 3 sigma rule. Okay, that's the 3 sigma rule. And, so this 3 sigma rule is very handy in practice, that if you have any random variable, the chances are approximately 90% that when you run your experiment, you will see a result that's within 3 sigma of the expected value. So now that, seals the deal on the way we are summarizing our complex experiment. The expected value, okay, tells us what we will see in the long run on an average basis. Okay. But then once we combine the expected value with 3 sigma, it also tells us what we are likely to see on a single experiment. When you run the experiment once, okay, 90% of the time, okay, you will observe something within 3 sigma of the expected value. And when sigma is small, the expected value is a very good summary of the experiment. Okay? And so deviations from the mean are controlled by this guy sigma, the standard deviation, which is the variance. Okay, so that more or less marks the end, in some sense, of the module on probability. Okay, and we ended with this concept that the expected value is a very important summary of an experiment. Okay? And how good a summary of an experiment it is depends on the standard deviation. Now let me show you a little bit of that in action, in practice. Okay, so we did the average of n dice. So the average of n dice. Average of n dice. Okay, and we computed the expected value of the average was equal to 3.5, and we computed the variance of the average. We did this earlier. The variance of the average was equal to 1 over n times 5 and 5/6. So 1 over n times the constant. So sigma, the square root of the variance, was equal to 1 over square root of n, okay, times the square root of 5 and 5/6. Okay. So when you run the experiment, you expect to see 3.5. Okay, and if we apply the 3 sigma rule, plus or minus 3 times this sigma, plus or minus 3 square root of 5 and 5/6 over square root of n. So this is an error bar. 3.5 plus or minus this error bar, but look at this error bar. Okay, so if this is 3.5, okay, and this is n, okay, then your 3.5 plus or minus 3 over root n, so a constant over root n is going to behave like that. So your error bar is approaching the expected value like 1 over root n. And so you expect to see values that look like that. Okay, shrinking closer and closer to the expected value as you get the average of more and more dice. Let me show you in practice. So remember this experiment I showed you at the beginning where I rolled n dice and took the average, and I showed you, what the average looked like for different choices of n in my experiment, and you see that it was converging closer and closer to the expected value, and the error bar, so this error bar is, mu, plus or minus 3 sigma. this number. And you see there, shaded in gray is the error bar. And look at how nicely the experiment follows the error bar. So what does the error bar show you? The error bar shows you the application of the 3 sigma rule. It says that, the observed average is within 3 sigma of the mean, which is 3.5. So that's the theory in practice. The theory works in practice. And so, the mean is a good summary up to plus or minus 3 times the standard deviation. Checking out.